Yeah, it's our pleasure to have like Yuxuan to talk about his work in demystify problem dependence, um, power of quantum neural network on multi class classifications. Yeah. So for this one, basically Yuxuan they utilize the statistical learning theory to understand why for quantum classifiers, the training loss might be more important than the generation errors. And then there were also studies the U-shaped risk curve, and then trying to compare with the double descent risk curve of like deep neural network classifiers. I guess like I will like pass the floor to Yuxuan and you may start the talks. Yeah.
Okay, thanks for invitation and introduction. Today, I'd like to share my talk, Demystify problem-dependent power of quantum neural networks on multi-class classification. To start the talk, I'd like to first reviewing the milestones of classical AI and quantum AI. And we can see in the upper panel, since from 1957, the perceptron is proposed. At that time, we can only handle tens of parameters in a learning model. And then 30 years later, the multilayer perceptron with backpropagation is proposed. From that now we can train like hundreds of parameters very efficiently. And maybe 40 years later, the AliceNet is proposed, which is built upon convolutional neural networks. And in 2012, big news is people use AliceNet to obtain the champion in image classification competitions. And at that time, people realized that deep neural networks maybe solve some practical problems in the world. And 8 years later, and in 2020, and to now, we find generative pre-trained transformer like ChatGPT and GPT-4 revolutionize the world. And it seems like a big model is a correct way towards artificial general intelligence, and we can step into the super AI world. The lower panel introduces the history of quantum AI. It has a much shorter history than classical AI. The first famous algorithm, quantum machine learning algorithm, is quantum linear grid solver proposed by Harrow. And its key backbone is quantum Fourier transformation. And use this backbone, the quantum principal component analysis and quantum support vector machine are proposed. A key feature of this class of quantum algorithm is that they are fault tolerant based, which means they require implement this algorithm on a fault-tolerant quantum computer. And the algorithm requires a deep circuit depth, and the quantum realm is necessary to achieve the exponential speed up. But we know fault-tolerant quantum computer is hard to fabricate. And this is a reason why we want to develop another method of quantum machine learning algorithms, which is called variational quantum algorithms. Variational quantum algorithms, the first one is proposed in 2014, which is named variational quantum eigensolver and quantum approximate optimization algorithm. And in 2018, the quantum neural network were proposed, and their variants are proposed in the following years. A key feature of variational quantum algorithm is that they are NISQ friendly, which means they don't require very deep circuit depth, and they don't require quantum realm. This provides an opportunity to use current quantum hardware to find some potential applications. And a key issue is which one is the correct path towards a super quantum AI world. We don't know the answer. This is why we want to study here, or why we want to use some theoretical results to understand the power of fault-tolerant-based quantum algorithms or variational-based quantum algorithms. Another reason why we are so interested in quantum neural networks is because it has a high similarity with deep neural networks. As we can see, why deep neural networks can deal with billions of data very effectively. It's because deep neural networks use a strategy called space and time trade-off, which means that in the big data era, we cannot load the whole data set to a training model, a learning model to get the target result. An alternative strategy is at each time we load a part of data into the learning model and using an iterative method. In this way, we can still let the learning model to see the whole data set, and we can get a good estimation of the target result. The similarity issue also encountered in quantum neural networks because, as aforementioned, quantum neural networks if we want to implement quantum networks on these devices, because these devices have very limited number of qubits and very limited circuit depth. So what we should do is control the computational burden or the number of data in it. So quantum neural networks also adopt the trade-off of the space and memory space and the time issue, and we can iteratively find a good estimation of the target result. Since it's adaptivity, flexibility, and the trade-off between the time and the memory space, we can implement variational quantum algorithm, which is called quantum neural networks on mixed devices to explore its potential applications. As summarized in the middle panel, experiment researchers have used variational quantum algorithm to explore how to use quantum computers to solve quantum chemistry problems, machine learning problems, like combinatorial optimization problems, or some new frontiers problems in quantum information, quantum metrology, or quantum foundations. So we may ask, if we have some advanced quantum hardware, like we have thousands of qubits and the circuit depth is sufficiently deep, if we implement over parameterized quantum neural networks on it, can we achieve the similar achievements like deep neural networks? So what we mean is, can we step into the quantum artificial general intelligence just by using quantum neural networks? And the result is, for optimization tasks, the result is mostly positive. But when the study problem is a learning problem, we have both positive and negative results. The key difference between optimization and learning of quantum neural networks is as follows, summarized in this figure. Because when we want to use quantum computer, especially quantum neural networks, to solve an optimization problem, we only need to consider the trainability and the specificity. The trainability means that the obtained result output by quantum neural network, how it close to the optimal result, which means the global minima of the loss function or cost function. And the specificity considers if the global minima can refer to the target solution. Fortunately, in most optimization problems like ground state preparation, if we adopt a very deep ansatz, which means we have exponentially many trainable parameters, we can always cover this target state. So what we need to understand is how to optimize the trainable parameters to fast converge to the global minima. So this is an issue considered in optimization. But for learning problems, the task is more difficult because we need to consider three factors, which means expressivity, trainability, and the generalization. Generalization means that we want to use a learning model to train a classifier. This classifier will separate the test data, not only the train data. When we use quantum neural networks to solve learning problem, an important issue is the target solution may not locate in its hypothetical space, which means that although you can find a global minima, but its global minima not correspond to the target solution. So this is the key difference between the optimization and the learning problems encountered in quantum networks. So based on the above understanding, I'd like to show some good news about optimization. Especially typical examples are ground state preparation and ground energy estimation. This is broadly encountered in quantum chemistry, quantum many-body physics, and combinatorial optimization. The problem is given an n-qubit Hamiltonian H. We want to find its ground energy E0 and ground state phi star. And the ground energy means the minimum eigenvalue of the matrix H, and the ground state means its corresponding eigenvector. And when we want to use quantum network to solve this optimization problem, what we do is we first use an ansatz to create a parameterized quantum state by theta and form a loss function defined here, which is operate the Hamiltonian with this parameterized quantum state. What we do is we first get this measured value and feed it into a classical machine. The classical machine want to update the trainable parameter theta to minimize this cost function. During t iterations, we can get an optimized parameter theta t. And what we want to know is whether theta t, the parameterized state by theta t can well approximate the target state phi star. And there are many challenges in using quantum neural networks to solve this problem because the loss landscape, I mean here, this loss function is non-convex, and we may encounter barren plateaus if the select u theta is not properly chosen. And we have many choices about the ansatz, like hardware efficient ansatz or Hamiltonian based ansatz. And we also have many initialization methods, which means how to initialize this theta 0. And optimization methods are also diverse, like zero order gradient descent, first order gradient descent. So how to choose a good learning model to solve arbitrary Hamiltonian, which means that we want to find a generic way. No matter how the Hamiltonian H is, we can always use these quantum networks to find a good estimation of phi theta star. And now we have some good news, which is called quantum neural intelligence kernel. The key idea is when we select the ansatz, we need to ensure its number of parameters is exponentially scale with the number of qubits, and we need to set the learning rate very small. In this way, we can always guarantee the obtained phi theta t can well approximate the target state y theta star in a controllable error epsilon. The detailed settings is listed here. Moreover, if we know the structure of the Hamiltonian in advance, we can also use this symmetry property to further reduce the number of parameters theta, maybe like 2 square root n. This is a very amazing result about how to use quantum neural networks to solve optimization problems. But when we use quantum neural networks to solve learning problems, we encounter many issues, because the key difference between the optimization and learning is data loading problem and the requirement of nonlinearity. The data loading problem is listed here. When we want to load classical data into quantum states, we generally have two choices. The first one is use ampli encoding, but this method may be very resource insensitive. We may need to use very deep secret depths to embed the classical information into the amplitudes of quantum states. Another choice is use gate embedding, which means that we can load classical data into the quantum gate instead of the amplitude. But this method also has a drawback, as listed here. For example, if we want to load 8 times 8 images into the quantum states, we require 64 qubits. This is too much. Another issue is if we use this very deep circuit, we may encounter like barren plateaus. Another issue is nonlinearity. nonlinearity is we want to map input data into any complex high-dimensional feature space. This is necessary for learning classical patterns, which may be very complex. But if we want to introduce nonlinearity into quantum circuits, it's very difficult because quantum mechanics is linear. So the only way we can involve nonlinearity into quantum circuit is using gate embedding. In this way, we can introduce a little bit nonlinearity. But for classical deep neural networks, it's very easier. We can just insert some nonlinear layers into your neural networks. So this difference results different behaviors of classical and quantum neural networks in learning classical data. As listed here, we have done many benchmarks to use both classical and quantum neural networks to learn different data sets. As we can see, if the data sets are from classical data like MNIST or Y dataset, quantum classifier are inferior to the classical neural networks like multilayer perceptron or convolutional neural networks. But if we use these two learning models to learn quantum data, which means the data is collected from quantum circuit, and then we can see quantum classifier has better performance than classical classifier. So we can conclude that maybe quantum classifier and quantum and classical classifier, they represent different process space. If the learning problem fall into this region, we can say quantum classifier are inferior to the classical classifiers. But if the problem falls into this region, maybe we can see potential quantum advantages. So due to these observations, we may ask, what's the foundation of quantum neural networks in learning both classical and quantum data? And our answer is the power of quantum neural network is problem dependent. And this claim is mainly based on our recent paper, and as shown here. So why we focus our study on the multi-class classification? This is because many foundational problems in classical and quantum worlds can be recast to classification tasks. For example, image classification, text classification, speech classification, and in quantum physics, the phase transition problems can also be understood as a classification task. So another issue I like to first address is what we have achieved in this paper. And there are mainly 6 achievements. The first one is we unify the trainability, generalization, and specificity into a same mathematical framework. And under this framework, we can interpret the trainability of quantum classifiers from a geometric view and use this view to link some results in quantum state theory and quantum measurement theory. And then the third achievement is we derive a non-vacuous generalization error bound of quantum classifiers, even for our parameterized region. And the fourth achievement is we unveil a trainability is more domestic rather than the generalization ability of quantum classifiers. And the fifth achievement is showing the disparate risk curves between classical and quantum classifiers. And the last is we devise an effective method to examine the power of quantum circuits. To better understand our results, I need to introduce some tedious notations about what is K-class classification and what is quantum classifier. So in the following slides, I set the input data space as X and the label space as Y. And we set the training data set as D, and each example is denoted here is XIK, and its label is YIK. And we suppose this training data set is balanced, which means that the example in each class is equal. So the total number of training data set is K times NK. And when we want to use an algorithm to solve a K-class classification task, This algorithm can either be quantum or classical. And we want to use this algorithm A to learn training dataset D to infer a hypothesis H. This hypothesis can well separate examples sampling from the space X times Y to the corresponding classes. And the optimal hypothesis is the one that minimizes the expected risk defined here. Here, the notation L denotes the per sample loss. In this paper, we specify it as the mean square loss, and D refers to the distribution of the data space X times Y. It may be noteworthy that this distribution D is generally unknown, so we cannot directly calculate the expected risk. So what we do is we use an alternative way is minimize the empirical risk. The loss function is defined here, which means that we not use the whole data set from its underlying distribution, but focus on the training data set and minimize this loss function. This term is the regularization term. For example, in deep neural networks, it can be referred to the L2 norm of the training ball parameters to avoid overfitting. And this is the basic notations and definitions of K-class classification and some background of hypothesis, expected risk, and empirical risk. And due to the fundamental role of the expected risk, so we can use this quantity to understand the power of quantum classifiers, which means that given a learning problem, when we use a classifier to infer an empirical classifier denoted by H hat C, and when we use a quantum classifier, learn an empirical classifier denoted by H hat Q, if the expected risk follows this condition, means that the expected risk of the quantum classifier is less than the classical classifier. We can claim in this learning problem, quantum classifier achieve potential advantages. But as aforementioned, the expected risk is hard to calculate. So we need to decompose it into two tractable terms. The one is empirical risk, another one is generalization. These two quantities refer to the trainability and the generalization mentioned before. And in classical machine learning community, we have a lot of results about the risk curve of deep neural networks, as listed in this picture, which means that when we continuously increase the hypothesis space, we can experience a double descent curve. Here, capacity of the hypothesis H means we can continuously increase the model size, means we can create a very deep neural networks. And we can see both the training risk and the test risk. Test risk means to the generalization error can tend to be zero, and we can get a zero expected risk. This delivers a message why we create GPT-4 use billions of parameters, because bigger model give you a better performance. A natural question is whether quantum classifiers also experience this behavior, which means that when we continuously enlarge the model size, we can also get a double descent curve. If this curve happens for quantum classifier, we can also get a general rule to solve any problem with theoretical guarantee. So to answer this question, we need to formalize the mathematical expression of quantum classifiers as listed here. I just gave some intuitions about these notations, and the details can be found in the paper. Recall both classical and quantum classifiers is used to minimize this empirical loss. The key difference is how to get this estimate prediction y hat ik for the xik. The ik is input example, and for quantum classifier, we get this following this structure, which means that y hat ik is denoted here. For its case entry, we just load the corresponding input example xik to the circuit and operate it with ansatz u theta, and measure it using the O-case measurement operator, get its prediction results. And then we can compare this vector, prediction vector, and the true vector to get a per sample loss. This is the basic structure of the quantum classifier. Note that here we didn't risk the layout of the employed ansatz. So it can be arbitrary architecture, and we only focus it contains anti-trainable parameters, and it contains some entangled layers. So this definition covers many typical ansatz such as tensor network-based ansatz, hardware-based ansatz, or some Hamiltonian-based ansatz. And the encoding circuit also follows this form, and we only care how many encoding gates are used to load classical data into the quantum circuit, and we denote this number as NG. And as we can see, because quantum classifier has many diverse structures, so if we want to get some general rule of this quantum classifiers, we need to first unify them in a simple structure. And this is what we've done here. What we do is we just focus on the state before the measurement, because no matter how you select your encoding circuit, UX, or the ansatz you theta, you must get some interesting feature state, which means the definition is stored here. So we can just partial trace the qubits that not interact with the non-trivial measurement operators, and focus the relations of the feature state and the measurement operators. And based on these definitions, we get some interesting results. What we want to know is under this unified quantum classifiers, under what conditions we can get zero expected risk. The conditions is listed in theorem 1. Specifically, when the training data set scales with OKNG, NG means the number of encoding gates, and when the feature state rho and the measurement operator O satisfy the following 3 conditions, we can have with probability 1 minus delta, the expected risk of quantum classifier tend to be 0. And the geometrical interpretation of these 3 conditions is visualized here. And this has many implications with the results in both classical deep learning theory and the results in some quantum information theories, as listed here. The first thing I want to address is the scaling behavior of the training data sets. As we can see, it's not too bad because N only polynomially depends on the number of classes and the number of encoding gates. Means that we can get a very low generalization error, even when only few training data are available. So this is good news. And another issue is the conditions 1, 2, 3 listed here. Which means how to get a perfect training, which means how to get your empirical risk tends to be 0. Following this geometrical interpretation, we can conclude that when the perfect training happens, which means the loss function tends to be 0, we can say the feature states have vanished by variability in the same class, which means that all the feature states in the same class concentrate to their mean features. And the second condition means all feature states are equivalent and are orthogonal in the very classes, which forms this structure. And the third condition is any feature state is alignment with the measurement operator in the same class. So this is why we list like rho bar 1 and O1 in the same direction. So this, from the classical deep learning view, this geometrical understanding is coincide with the neural collapse phenomena encountered in deep networks. The neural network collapse, this phenomenon means that when the perfect training happens for deep networks, we can see the feature state in the last second layer also follows this geometrical structure. And this geometry from a quantum view, we can understand that we can connect this result with quantitative discrimination, which means that for any 2 varied classes like O star k and O star k prime, it can classify rho bar k and rho bar k prime with probability 1. this maximizes the Helstrom bound. As you can see, 0.1 stress that the impure risk dominates the expected risk because the generalization error can be easily tend to be 0, but we don't know how to satisfy these three geometry conditions. So in other words, given a quantum classifier, its ability and limitations can be quantified by examining whether these three conditions can be fulfilled. So in this field, we derive following corollary to show the fundamental limitations of over-parameterized quantum circuits. This quantum classifiers, this is listed in corollary 1, which means that when the encoding unitary is too deep following the hard distribution with probably 1 minus delta, we can say the feature states concentrates to the same direction. And this collapses the condition 1. And when the implied ansatz is too deep, following a hard distribution with probability 1 minus delta, we can say the measurement operator are in the same direction. This collapses the condition 3. So taken altogether, we can conclude that there is no perfect training for over-parameterized quantum circuits. So when we adopt over-parameterized quantum classifier, we will experience a U-shaped risk curve instead of the double descent risk curve encountered in deep neural networks. And we can see there is a little difference of this U-shaped curve because in classical deep networks, the U-shaped curve is incurred by the test risk, which means that when we increase the capacity of hypothesis, the generalization becomes large and the expected risk becomes large. But for quantum classifiers, the U-shaped risk curve is incurred by the training risk, which means that we can't get a perfect training. The training loss is still very large, so the expected risk becomes very large. So the distinct behavior between quantum classifiers and classical classifiers in the view of risk curve give these following results. The first is the separation of variational quantum algorithms or quantum neural networks in optimization and learning. Because as mentioned above, our parameterization used in neural tangent kernel is the key of you to achieve an optimal result for any Hamiltonian H, but it forbids the optimal learning. So this is a key difference. And what's the general method to achieve perfect training for learning tasks is still an open question. And the second implication is shown here. Because we have prior information about the risk curve between quantum and classical classifiers, so we can devise an efficient algorithm to detect the power of quantum classifiers, which means that we can see the most region with quantum advantages is at here, which means the modest hypothesis space. So we can just fit in this risk curve and find the minimum one and compare this region with classical classifiers to locate potential advantages. And the detailed algorithm is provided in the paper named Algorithm 1, page 20. And I just give some proof sketch of the Silver 1, and the details can be found in the paper. As we can see, if we want to prove the expected risk tends to be 0, we need to decompose it to two tractable terms, the empirical risk and the generalization error. So in the proof, we just separated analysis the conditions when the empirical risk can be tends to be 0, and when the underworld conditions, the generalization error G and E can be tends to be 0. And for the setting when the empirical risk can be tends to 0, we consider two settings. The first setting is both the feature states rho and the measurement operators all can be both can be trainable. And the result is shown in number 1. What we conclude is that when the regularization term is considered and the optimized feature state rho and O meets 3 conditions in theorem 1, the empirical risk is C1 square divided by 2, where C1 depends on the hyperparameter in the regularization term. And the second setting, we consider only feature state is tunable and the measurement operator is predefined. In this setting, we calculate when these 3 conditions are satisfied, the empirical risk can be turned to 0. And for the generalization, the result is shown in lemma 3. And we just need to combine these 3 lemma to obtain the result of theorem 1. And the proof sketch of lemma 1 and 2 is listed here. They are followed in the same insight, which means that these 3 conditions can be obtained by lower bounding the empirical laws listed here. And these conditions correspond to the equality conditions in the inequality. And we just need to continuously derive the lower bound and recognize when the inequality condition happens and to conclude these 3 conditions. And I just keep here. And to prove lemma 3, we use the definition of robustness. Robustness is defined here, which measures how much the loss value can be varied with respect to the input space Z. And as we can see here, the key insight is we need to decompose the input space Z into disjoint sets. As I noted before, because the input space is continuous, if we didn't declaration it will contain infinity terms. So how do we get disjoint sets? The method is using carving number. When we using carving number to calculate the disjoint sets, we're using lemma 2 to obtain that the disjoint sets CR is upper bounded by this term. And when we have the robustness quantity of the quantum classifier, we can just link it with the result in learning theory, which use robustness to bound the generated arrow, and we can get lemma 3. So the key issue in this theorem, in this lemma, is how to use link covering number unitary space and to get a pretty good result, a reasonable bound, upper bound. And the implications of lemma 3 is listed here. As we can see in this generalization upper bound, it doesn't depend on the number of trainable parameters. This is very important to use this bound to explain over parameterized generalization error, because in previous studies, we can see the generalization error is upper bound by the number of trainable gates, which means how many trainable variational quantum gates in the ansatz. So if we want to use this bound to understand the power of quantum classifiers, it will lead to a vacuous bound. It's non-meaningful. But our bound is more reasonable because it doesn't depend on this term. The second implication is our bound means that we need to carefully design encoding circuit UE because our bound depends on this term and number of encoding gates NGE. And the third implication is our bound is algorithm and data dependent, reflected by this term tau D. As we can see, the tau D definition I list here, it depends on the number of the disjoint sets CR. In the beginning of training, CR may be very large. It may be equals to the number of training data sets. But as we can see, when the perfect training happens, all feature states concentrate to the k vectors. This means that when we want to calculate the disjoint sets of this geometric picture, we can find this term tau D only equals to k instead of n. So this is very good news, which means that when you continuously optimize the quantum classifier, you can find the generalization bound, especially this term tau D, can be decreased. So this is why I say this is algorithm and data dependent. So this is the implication of our generalization error bound. And we conduct several two experiments to visualize our results, especially these two distinct risk curve. And the first experiment is binary classification on parity dataset. The dataset is listed here. We create in total 48 examples, and we label the bit string as 0 if the number of all in input example is even, and otherwise we label is 1. And we adopt answers as hardware efficient answers, and the number of layers controls the hypothesis space, and the measurements is predefined. We predefined two measurement operators, 0 basis and 1 basis, and as we neural collapse monomial happens, we can say all feature states concentrates to their class mean, and also concentrates to their measurement operator. And we compare the performance of quantum classifier and classical classifier on this dataset. The classical classifier is implemented by the multilayer Perceptron. As we can see, there is a U-shaped curve, and the quantum classifier is superior to the classical one. And the second experiment is using quantum classifier and convolutional neural network to learn an image dataset. And we set there are in total 9 classes, and in each classes, the training example, the number of training example is 18. And here is the performance, and we can see when we vary a hypothesis, we also experience a U-shaped curve of quantum classifier, but its impact risk is greatly larger than convolutional neural networks. So in this field, we may say there is no advantages when we use hardware efficient quantum classifier to learn image dataset, which means actually means dataset. So here is our experiment results. So what's the outlook of our result? Here are 3 interesting directions. The first is based on the different risk curves. So this motivates us to rethink if we need to create new quantum learning models that can experience perfect training. The second issue is if nonlinearity is necessary for quantum classifiers. Otherwise, we don't know how to get a double descent risk curve. And the third interesting direction is how to prove potential quantum advantages on quantum data, because as our first experiment shown, quantum classifiers can well learn parity dataset, but how to find some practical learning problems with provable advantages is an open question. And here is the reference list used in this slide. And thanks.
Yeah, thanks, Yuxuan, for the interesting talks. And like I like a lot about your introductions. It will kind of like tell us about like how different is the optimizations and the learnabilities of quantum neural network, and it's kind of like help me concretize my pictures.
Yeah.
So far I didn't see any question coming from audience. Maybe I could like start off with my some question from me. Can you go to the conclusion slides?
Okay.
Yeah, now I just like maybe just ask some question about conclusions. Like for the last one, right? I think Robert Huang from like John Preskill's group have a science paper showing that like quantum computers could like efficiently learn some quantum data compared to the classical machines, right?
Okay, I see, but their method doesn't depend on quantum neural network. They just show how to use entangled measurement to get some advantages, and their results mainly based on information theoretical results. But how to link quantum neural networks with their results is still an open question.
Right. Okay. Yeah. Then I'm clear now. What's the distinctions? Yeah. Yeah. And for the second one, it's pretty interesting because for last week, we have a speaker basically trying to incorporating non-linearity into quantum neural network and trying to use it to do generator modeling. So so what they use is basically using the repeat until success circuit and then use it as a quantum neurons. And this will be interesting to see like whether like this kind of model will give us a double descent curves and how it's like compared to the deep neural network or not. Yeah. Yeah. Yeah, as in, okay, so actually I have a couple of questions. So maybe if like for the audience, if you want to ask questions, then you can just like give a heads up, or or like type in the chat and I could address it. Otherwise, I will continue on with my questions. My questions are quite a lot. Because like you mentioned that for some problem you will be able to attempt perfect training, right? Like the first one. But then how we currently we are still unclear of whether we can get this to this like perfect training regime because of parameters, right? Like in any case we still have to train our circuit in order to reach this perfect training to do like perfect classifications, right?
Yeah, the perfect training depends on two terms, which means that perfect training there are two issues. The first is how to get the zero loss. This maybe doesn't depend on the optimizer method. This means that when you select answers, there is fundamental limitations of your convolutional networks, no matter how the optimization you choice. Which means that even you encounter barren plateaus, the neural technical kernel results showing that you can wait sufficient long times, you can still get optimal results, which means that I can show here. Here, as shown here, because neural technical kernel also use exponential parameters, so it must encounter barren plateaus. But it doesn't matter because when you use very deep answers, your loss shape in like this form, you have many local minima, and this local minima correspond to global minima, as we can say they are very close. So even though encounter barren plateau, means that your initialized parameters located here. And as we can see, barren plateau means the variance and the expectations of the gradients is very small. It's okay. We just need to iteration enough, and it can still goes down to a local minima, and you can get a pretty good result.
Right.
The fundamental issue of perfect training is that when you select very deep circuit, there you can never get this geometrical structure as I plot here, because the fundamental issue is when the concentration measure phenomenon will happen, and all useful feature states will have a same direction. So there are some distinctions about perfect training and barren plateaus. The one is understanding the fundamental limitation of your models, and barren plateaus concerns how to fast find a pretty good estimation result. So this is two different problems.
I see. Okay. Yeah. Got it. No problem. Right. Optimization. Right. So apart from these training questions, there have another questions. So you kind of like show that like for certain case, the empirical risk will the empirical risk will be go to zero, right? And this for me looks very much like what I call like the quantum method, the representative theorems, because like we know quantum neural network and quantum methods are actually like pretty much the same, and then you can like cast the quantum neural network as a subset of quantum kernel machines. So is that any relation between your results and the representation theorem?
Okay. I think there is a recent paper published in Nature Communication. It discussed the connection between quantum kernel, quantum neural network, and the re-uploading methods.
Oh,
and
right.
this paper,
Sophie, right?
yeah, I think we can just combine their results with the results present here, and we see at least these three models are equivalent when you use enough resources, such as if you don't use reuploading, when you have exponentially many qubits, their expected power is equivalent. So, and as for kernel, their conclusion is that the quantum kernel method are inferior to quantum neural networks. So we can just use their results to better understand like representation theory and how to get perfect training. I think they can generalize because these three models have some equivalent relation, and we just to get some perfect training on one model and generalize this result to the rest two models.
Right. Yeah. Actually, my current project is also working in this direction. Basically, one of the results that I obtained is basically found a way to combine especially show that the relationship between like quantum neural network and quantum kernel machines. Yeah, and the way that I define is pretty much similar with how you define your feature state. Yeah.
Yeah.
So yeah, now I'm still writing up the papers, and maybe we can talk more once the paper is out and trying to see like what is the relationship between like our methods and stuff like that. Yeah. Yeah. So the other things that I kind of have questions is about the concentrations like result that you have. Like I know it's like there was also one concentration results in quantum kernels methods by Suparnot and Zoe's Holmes.
Yeah.
Yeah. So they kind of like study different kind of concentrate like different sources of concentration, right? Like one is like expressivities, and so I guess is also kind of has some relation with their papers, I would say.
Yeah, I see this paper. They just discussed how the number of measurements, noise, and the expressivity incur the concentration phenomena of the quantum kernel. Yeah, and this result is very similar conclude here.
Yeah.
Because both if we want to load classical into quantum circuits, we must to find a way to encoding it, and a general way is gate encoding. Gate encoding, when we want to load a high dimensional feature into it, it's encounter the same issue as the ansatz, because both if it's high dimensional, you use very deep secrets and you use many qubits, it's also for the hard distribution. We can use result from unitary TDI to get the concentration measure results.
Right.
So it's in the mathematical view, the proof is very similar.
Right. Okay. Yeah.
Yeah.
Yeah. And yeah, it'll be interesting to see how things really just extend from one to the other. Yes. Okay. Seems like most of the questions are from me, and I guess the audience might need some time to like process your result, because like all of these are pretty interesting, and maybe some require some kind of like background to generate some questions. Then they might ask you afterwards about any questions that that have like about your paper. Now is like close to 11. Maybe if there's no further question, then we can just end the presentations. Yeah, thank you very much again, Yuxuan, for agreeing to talk in our seminars, and like looking forward to have you in our future seminar.
Okay, thank you.
Yep. See you.
See you. Bye.
Bye.